Welcome. We're to Chemistry 312, Organic Chemistry 2. I'll start with Chapter 17, Reactions of Aromatic Compounds. Last video, we talked about what it meant to be aromatic, and now we'll talk about the specialized reactions that we need to react with aromatics. So a lot of these classes of reactions will be called electrophilic aromatic substitutions. Basically, we're going to substitute one of the hydrogens on an aromatic compound with an electrophile. We need a really strong electrophile to attack here. So the class reaction adds electrophile to an aryl to form a sigma complex and removes a proton. So the generalized mechanism is as follows. So we have benzene, we have electrophile. It's going to, what is it? The lone pair is going to attack there. I mean, not the lone pair, but the pi bond is going to attack there. We're going to form the sigma complex. The sigma complex is going to be this resonance stabilized He. Put a positive charge there. It's going to be stabilized by the two other resonance structures. So we can essentially delocalize that cation. Plus there. And the other resonance structure has the positive charge up top. So the pi cloud still can move around. So we're essentially resonance stabilizing this with the positive charge either from the electrophile at the 2, the 4, or the 6 position with respect to the electrophile. At which point we add from that structure from there we have a base is going to then depronate that. Lone pair going to swing back down, and we're going to reform our aromatic. That's the generalized mechanism, regardless of what we're doing. So we're going to do several different classes of reactions. We're going to do various halogenations. We're going to do some nitrations, sulfonations, just to name a few. We'll eventually get to acylations and alkylations. We'll start with some of the easier ones. So the halogenations. Now, bromination, we have to form electrophile out of bromine. So we have to turn Br2 into Br plus. But we can do this by adding a Lewis acid. A Lewis acid is going to attract a Lewis base, and we're going to Lewis acid. We're going to do this with iron tribromide. If you did iron with any other thing, you might risk putting a different electrophile on. So what we want is we're going to form a Lewis acid adduct. Lewis adduct of FeBr4 1 minus and Br plus 1. Now this is our reactive No, sorry. I mean, the BR, that's our activator that's going to allow us to do the reaction. So once we have the Br plus 1, once we have the Br plus 1, we're going to say that the benzene plus bromine, we're going to form our intermediate plus H and Br, and then this activator is then going to revert this back to the next step. So that the bromine's going to leave there. It's the activator, but it's going to be a catalyst as well. So it's going to reform HBr. It's going to form HBr and FeBr3 again. So we have put on our bromine. So we're having difficulty doing just that, but as I said, our Lewis acid going to ease that up, make it easier to form that complex. Now, the formation of the sigma complex is endothermic, but the removal of H plus is exothermic. So the net reaction is exothermic. That when we add alkene double bromines across an alkene double bond, this is far more reactive. So these aromatic additions, we only see single addition, and it needs a Lewis acid. So that's how you can compare. And it's what we'll see is typically going to add at the ortho and para positions, especially if it's already substituted. But we'll see this in a minute. So this is, we need heat plus enthalpy, but at this final step, we're going to get plus a lot of heat right back. Okay. Chlorination. Chlorination is very similar. We just use a slightly different Lewis acid. Same mechanism. We're going to add chlorine, and we're going to have a Lewis acid catalyst, aluminum trichloride, very similar to iron tribromide. The net result is we're going to form chlorobenzene and HCl. Very similar, just requires a different Lewis acid. Iodination. The iodine is a little bit different. It's going to need a acidic oxidant. This one is not catalytic. This is not catalytic, so it actually requires a reactor. So we're going to have a half equivalent of iodine, nitric acid. The nitric acid is going to, and in acidic medium, it's going to form our iodine. Iodobenzene, it's going to form NO2 gas and water. The actual reactive mechanism, I mean, it starts very similar. You have H plus, we have to activate our iodine. H plus and HNO3 and our iodo. It's going to split it into I plus and NO2 and our water. So it's essentially that the nitric acid is going to gain an electron from iodine. It's going to oxidize iodine to form that. And so HNO3 goes to NO2. So it goes, nitrogen goes from 5 plus to 4 plus, while iodine goes from 0 to 1 plus. And so that's essentially, that is completely different. And if you remember back to when we tried to add iodine onto various compounds, bromine was really easy, chlorine was relatively easy, iodine usually took a different method. Something about its stability and all that. Now, nitration. Nitration can be done several different ways. You can use nitration just with concentrated, so lots of nitric acid and lots of heat, and that will form NO2. But this is toxic, dangerous, not really good. A safer method is using another acid as a catalyst. So the safer method is just we add HNO3 stoichiometric quantities, and we have H2SO4 as our catalyst. The basic thing is that we can do this. It's fast, and it can be done at a much lower temperature, much more safely. Much more safely. And it basically works on we're forming nitronium, NO2 plus 1. So how does that happen? It all comes down, as I said, the sigma complex, but we have to activate our catalyst. We have to activate our electrophile first. So we have this structure. Drawing, hopefully you know what nitric acid looks like. Minus. Oh. And plus on the N. In the presence of sulfuric acid. So H O S O H2SO4. I'm going to leave off the lone pairs from the rest of them just because otherwise it's going to take forever. So we swing that down, attacks here. Forms an intermediate of pronated water. Now it's something good leaving group. Very good leaving group. Especially with two positive charges so darn close together. And HSO4. So lone pair can swing down, make the double bond, kick that off. So we form water, 2O, and our NO2. It's still plus charge. And there's our nitronium. Now, at this point, our benzene comes in. We attack the nitrogen. And it splits back into sigma. It goes into our sigma complex. O minus plus. And then the sulfuric acid catalyst. HSO4 minus. Basic enough that it can extract that. I mean, you normally think H2SO4 is a strong acid. H2SO4 is a strong acid. It doesn't necessarily want to take a proton, but it is a strong acid in water. In water, it's stronger acid than water. In different substances, it could be considered a weaker acid. In this organic compound, the sigma complex has a very acidic proton. It wants to do whatever it can to kick off that hydrogen. It'd much rather lose that hydrogen than than not. I mean, it's essentially, it's not going to go backwards. We're not going to pronate a benzene. So this is a very acidic thing. It'd rather reform the aromaticity, and that highly exothermic reforming of the aromaticity is what's going to allow this to be so acidic and drop off that proton again. Now, why is this really important? Nitroso compound, not super useful. It depends on what you want, but not always the best compound. But here's a big thing. You want to write this down if you can. And nitroso can be reduced to an amine. Amine by doing two things. You put a metal and HCl. HCl and a metal. Metal includes zinc / tin or iron, and HCl, and you get an aniline, which is NH2. Maybe it'll be pronated, but you have to depronate it. But the big thing here is we don't have a reaction that will add an amine onto the benzene ring. So if you ever find you need to add amine on the benzene ring, what do you have to do? You have to add the nitro group first and then reduce it to an aniline, to that amine. So think about that. In stepwise reactions, you're like, I don't know how to add that. I just can't add that. Well, you got to think, can I add something similar and convert it? That's a lot of this. Sulfonation. We're going to add on SO3H, essentially like a tosyl group. We're going to add sulfonic acid. You have aryl sulfonic acid. The basic reaction is, in this case, our structure is SO3, and we're going to using H2SO4. Electrophile is SO3. 4 is a catalyst. We're going to form the sigma complex. S O minus O. Oh, for God's sake. 3, and we're gonna then use the base, the HSO4, to depronate it. HSO4 minus to get down to here. SO1 minus O. No. And of course, the SO1 minus is acidic. So in the presence of H2SO4, which we do have, it's going to be pronated. So our ending product is the benzene sulfonic acid. So benzene sulfonic acid. So that is a basic oxygen. Now, this is useful. This is actually a pretty good protecting group because while this is good to add, it is easy enough to get off. So, one of the things is of a protecting group is easy to add, resistant to reaction, and easy to remove again. So, in the presence of acid and heat, so like steam. So, steam, we can crack this back down to benzene and H2SO4. So it's the same path as a sulfonation, but in reverse. Same path as a sulfonation, but in reverse. So heat, we're essentially popping it back, pronating here, pronating on the sigma complex, and allowing that to bust off. Now, this could be useful because it's possible to have a deuterium, hydrogen to deuterium exchange. Remember, deuterium is that 1 proton, 1 neutron hydrogen. So if you use, instead of H plus in steam, you could use D plus in steam. You could essentially replace all of the, you do this enough times to enough positions, you're going to essentially replace all the hydrogens around the benzene with deuteriums. This allows you to get NMR solvent, C6D6, deuterated benzene. So, yeah, I mean, that's the essential process. If I do D2SO4 and D2O, you're eventually going to get C6D6. Now, there's some important effects we need to worry about because there are such things as activating and deactivating effects. That when we substitute these guys, they can often keep reacting. But, and we'll see that. If we look at it, when we look at the effect of alkyl substitution, toluene reacts, toluene reacts is 2.5 times faster than just benzene. That's because what we're going to say, this is activated. If I want to add electrophile on there, it reacts 2.5 times faster. If I look at nitration, produces a mixture of products. So if I try to nitrate a toluene, try to nitrate this. If I try to nitrate this, so I'm going to put that into, we have two different ortho products. Two different meta positions and one para. And looking at that, when we nitrate that, 2 ortho is 60%. The meta is 4%, and para is 36% of the product yield for the nitration of toluene. Now, just based on what we know about sterics and what we know about probability, if you look at just probability's sake, 5 different possibilities, you would expect every possibility to be 20%. 20%. If you look at sterics, you'd expect ortho to be one of the lowest possibilities. Instead, it is each ortho is essentially 30% of the possibilities. Para is higher than ortho because of sterics, but you would not expect meta to be so low. You would not expect meta to be so low. So there is something else going on here, and that is a methyl group, in this case for our toluene, is what we call an ortho-para director, meaning it's going to push any substitution preferably onto the ortho and para position. Does that mean we do not get any meta? No. But it does mean meta is highly disfavored. And this is because if we look at the sigma complexes on this, you'll see one thing particularly happens on here. So let's draw the ortho, meta, and para sigma complexes for this guy. So just looking at, I got it wrong, benzene, because we have 3 sigma complexes for each structure. Well, actually, I'll just put electrophile. So let's look at the orthos. Okay. We can draw put that guy there. That guy there. Okay. Of the ortho, there is 3 sigma complexes, but one of them has the positive charge attached to the carbon that is bound to the methyl. What do we know about methyl groups? Methyl groups are electron donors, and they are known to stabilize carbocations. We know that because if you look at a secondary carbocation versus a tertiary carbocation, the more carbons we add, the more stable the carbocation. We'll look at the same thing, para. We have a more stable carbocation. Okay. So in this case, I'll put the positive charge here. In this case, positive charge here. Bam. And positive charge here. In this case, one of these 3 structures has the positive charge attached to the methyl group. Once again, stabilizing one of these. These sigma complexes, this one is the favored complex. This one is a favored complex. What that does is it lowers the activation energy. It's not that the others are necessarily the other ones are essentially higher energy, and so these things are going to make the formation that much easier. If we look at meta, meta is going to have a completely different setup. H. Gotta draw them. Wish it was easier, but it's what I got. H. So positive charge there. Bam, bam. Positive charge here. Bam, bam. And the positive charge there. So none of these structures are particularly favored. Methyl is electron donating. It's going to stabilize the rate determining step. This large, remember, sigma complex is a large endothermic step. The reformation of the aromatic is a large exothermic step. So the rate determining step is the formation of the sigma products. So whenever one intermediate is favored, that's essentially going to lower the activation energy barrier, make this go so much faster. With meta, no one complex is particularly favored. So what we see is a higher activation energy barrier. So ortho, if you're looking at this, we have we have, we have let's say maybe meta. We have ortho. Boom. We got para. Boom. So meta's not going to really want to react at all. Well, ortho, very much so. And para, very much so. So these are what's called ortho para directors. Now, there's several different types of ortho para directors, but they all kind of follow a similar thing of electron donating. Of the ortho para directors, we can have alkyl groups of all type. Alkyl. Donate E. Just inductive stabilization. We could have substituents with lone pairs. Those are also a good choice. So OR, OH, NH2. These guys are all good because essentially what do they do? If I have a structure that looks like this, OH, this may be a, oh, yeah, let's erase this. Shoot, erased too much, but okay. I got it. In the case of ortho EH. So if I put the plus right here, we can resonance between that complex and this complex. Try to keep the stereochemistry the same. OH. Pair, lone pair. Put the plus on the oxygen. Now, that may not be a particularly stable resonance structure, but it's an extra resonance structure that has some help. It's going to assist in stabilizing and favoring this complex. It may not be the best, but it will help. So any resonance stabilization, oxygen is resonance donating. It's a pi donating thing. So in terms of strength of orthopara directors, we have an alkoxide is better than a tertiary amine. Well, I think maybe amine of any type, which is better than OH, which is better than OR, which is better than a amide, which is better than an alkyl. So those are our classes. So O minus, the most negative character, most easily in sharing the electrons. NR2. N is a lot easier to share the electrons than oxygen because of, the whole less electronegative, better able to hold a positive. And of course, if it has any R groups, stabilize that. Then OH and OR. And an amide, less stable because you have what we're going to see the aldehydic group, the carbonyl group is going to be electron withdrawing, and it's going to pull electron density away. And so in that way, it's going to destabilize this a bit. Still, that resonance structure will have some effect. So all these are Orthopara directors. That's where we're going to end this video. Thank you for your time. We'll finish up this chapter next video.